Okay, our next talk will be by G Goavec, and he's talking to us about platform-independent CPU FPGA co-design.
Thank you. This talk is about this ecosystem. We have developed an ecosystem to be able to assemble and generate design in the FPGA and using the CPU for example, on the Zinc board, the CPU to configure the design and to configure each block at the runtime. It's possible to modify some parameters in live. It's fully pipelined. It's not no FIFO, nothing. It's just a sample arrive is used. So we try at possible to avoid using RAM to simplify design. Since we use a CPU with Linux, this ecosystem complies with the structure of an architecture of operating system. We have a drive IP are connected to the CPU to communicate with respect of system, and in the better way we provide driver for these IPs. And finally, some IPs are some complex configurations, so we provide again library to avoid to duplicate piece of code. It's more the user has to focus on the design, on the application, and nothing else. The last wish about this framework is to be as possible independent of the hardware. The same design must be generate for a Zinc platform, for a Cyclone 5 platform, and maybe other new one existing. We are validated. It's not exhaustive on Zinc, on Cyclone 5 with some different board. It's other board with other hardware, but it's some ID. It's not alone. There are other ecosystems. The first one, of course, is the Etus RFNOC used in the USRP. It's a great thing because your USRP has a firmware like a toolbox with some IPs available to be used. It's possible to configure which processing is done in the FPGA, which processing is done in the CPU by just adding RefNoc block or GNU radio block. But if your design has an IP you need for your specific application, you need to generate a new firmware with this IP. And the RefNoc structure has a limited slot available to add your IPs, 5 or 7, I don't remember exactly. And I have tried to use a RefNoc on a Z board with an A2D converter. Finally, the FPGA part, it's okay. It's not really hard. But UHD, it's a fail. UHD do some assumption about the hardware. You have an EDUPROM to detect the motherboard, the daughter board. You need to have an TX chain, a rake chain, and finally it's just too complex for some small design. So it's really good, but with USRP. Another ecosystem framework is Pavel Demin Red Pitaya Note. It's this ecosystem has been present here. The good thing about this ecosystem is the repository provides some already available design. You have just to do some make, and you have SD card ready to be used. Each project has a documentation with everything, and it's directly compatible with the GNU radio. Finally, Osmo SDR has a client for Red Pitaya CPU server part, and you have a Red Pitaya exactly as a DVB-T key, USRP or another. But it's dedicated to the Red Pitaya platform, and it's more or less limited to the already available project. It's to move from another board on or to create your your safe project, it's less documented. Okay, now the ecosystem look like this. We have the IPs. The IPs has a specific repository. The IPs is connected to the CPU using driver to communicate, library or not, and device tree, because with the SOC system, the way to describe a platform is the device tree, and this overlay is used to append the default runtime device tree. And finally, you provide some tools to build the application, to provide some wrapper, to generate some part of design. First thing, maybe the most important part is the FPGA and the IP. It's for simplified simulation. We have split between the implementation part, the algorithm implementation, and the rest, the communication for the configuration of the design. Exactly as GNU Radio, we use a custom interface. This allows the user to plug one block, to connect one block to one other, and it, thanks to this interface, it's okay. It's the coherent data stream. For the user, it's just a wire like this one, but to provide more information, we have in this interface this series of signal, data, control, and clock and reset to be sure to have a correct coherence with the cross-clock domain. More precisely about content, you have on a complex, you have INQ data bus, on real just one data, and enable to specify when a new data is available to be processed. And you have some control signals, starter frame, stopper frame. Finally, an 2D converter or D2A converter has just an infinite data stream. No start, no stop, nothing. But when you have some design with when we want to propagate data only on the event, it's mandatory to know the start sample, the end sample of the data set. It's exactly the same for example, the FFT. The FFT has the start frequency, stop frequency. And this two signal allows to simplify the logic per IP to handle this data set. Okay, we have the IP. Now we must connect the IP and generate the design. It's possible, of course, to use the graphical approach with Vivado or with Quartus and QSys, but all vendor tools provide some procedure to build a design using TCL. The interest of this is small, able to version, and it's a great thing. But Vivado provides some function, create DB, create BDCL, etc. It's a specific procedure for Vivado. It's the same thing for Quartus. And finally, Vivado need one TCL file to generate everything. Quartus need two files to generate everything. So we have added our procedure and some make file to generate. This, for example, this procedure is implemented in the Vivado context, in the Quartus context. If you want to add a new vendor tool, you need just to fill this procedure to be able to build the design for a new platform with a new tool. I've do some tests with two different FPGA and two different vendor tools. The same design, the same application is able to work in all cases. Some stuff are just generate for each platform, but it's not a problem. It's just generate. The rest is perfectly compatible. The design is just a subpart of a project. A project look like this. You have the project directory, subdirectory, where we store everything about the design. Once the design built, it's possible to use TCL script to analyze XPR or Quartus equivalent to extract which IPs are connected to the CPU, the base address for each of them, to generate an XML file. This XML file is used by a tool to generate a template of application. And the last thing for the user is just to create a C++ or Python file to configure everything in the FPGA. This set is generated by module generator. You have an XML file, you have a project name, you have an IP, a second IP. IP is the name of the IP in the repository. And for each of them, you have instance IP with a specific name, with a specific address. Based on this, it's possible to generate the script. Script is to simplify to simplify the run of the application. You copy the bitstream, you flash the FPGA, you update the device tree, you append your device tree with your specific case, and you load driver mandatory for this specific project. First one. Second, device tree. You need to append, and you find exactly, you append the FPGA full. It's a node dedicated to handle the FPGA. You have the firmware name. You have one driver with this same base address, is exactly the same. And finally, a makefile. Makefile is just used to cross-compile the application, to compile everything, and to install in the board everything. It's finally all about the ecosystem. Just we provide this block. It's not all block available, but it's subset. You have a local oscillator, frequency transposition. You have an IP used to handle A to D converter, a D to A converter for the red pitaya. You have a sound card. You have some block used to start the propagation when a specific event appears on the block, on the pin of the FPGA for a trigger event. You have a radio frequency signal, CA code used for GNSS GPS, FIR filter. You have FIR filter real for interface real, complex for interface complex, etc. Some PRN generator, a cross correlator, again used to, for example, with the GPS, and some utilities to add a specific constant to all sample received. It's exactly an offset. You have adder subtractor. You add one input to the other input, mean on a simple accumulator. And some utilities convert from one interface to another interface, in custom interface, duple, because interface is one-to-one, and sometimes we want to have one-to-many. So we have this to allow these possibilities. Expander shifter is for bit manipulating, for bit shifting or expanding. Switch is just a select. You have two inputs. You have MUX finally, and some interface between our custom interface and AXI interface used, for example, when you need to use a FIFO provided by Xilinx to do a cross-clock domain. Now we have seen the ecosystem, but why doing with? First one is the GPS decoding. The idea is we have a Pluto SDR. The Pluto SDR is able to directly sample the signal. We have a satellite constellation with the same carrier frequency, but with a Doppler shift, and with each satellite has a unique PRN code. But when you use the Pluto SDR, like this one, with the stock firmware, finally the Pluto SDR do quite nothing. Receive data, transmit data, and it's all. To detect which satellite is present, you need to loop on the frequency, you need to loop on the PRN, so you need to cross-correlate the signal with all possible PRN code. with a GNU radio on CPU, it takes 1 or 2 seconds per satellite. The idea is to update the firmware by adding our specific IP to do exactly the same thing, but in processing. This looks like this. You have your ref front end, the local oscillator of the RF front end take some time to reconfigure, to be reconfigured. So we have added NCO, a local oscillator, a mixer to do a second step frequency transposition. You have our CA code generator. This block provides all possible CA code in parallel. So we use the user space to configure our CA code to move to loop frequency and to select which parent we want to use. And you have the cross correlator, and the result is just sent to the RAM and received from the CPU. Thanks to finally, the most important thing, we have added this part, but we don't break anything. The Pluto works exactly like with a default firmware, but with a bonus block. Thanks to this modification, it's possible to divide by 5 the time to process all satellites for all frequency. But now, we are just limited by the zinc. The FPGA part is a bit small, so it's not possible to add more than 1 cross correlator in the FPGA. So we have moved on the analog device board with the biggest FPGA to be able to cross-correlate all satellites at the same time. It's a work in progress. Currently, the design fits in the FPGA in parallel on the official data stream, but we need just to verify it's working. Next demonstration is it's more funny demonstration. Again, the Pluto SDR do quite nothing, and but this board use built root to generate the firmware, the root file system, the Linux system, etc. Built root support GNU radio, so it's possible to add GNU radio in the firmware on the board. We have do this, and the second idea is to have really totally embedded. So we have added a sound card in parallel in the FPGA. And finally, we have an application, C++, Python, what you want, to do this low pass filter, WFM receiver, and output on the sound card. This looks like this. You have the default RX chain, the IIO used as a sink, as a source, by GNU radio. The process is done by GNU radio, and an audio sync is used connected to the ALSA framework. We provide a driver compatible ALSA to communicate with the Sigma Delta IP in the FPGA and RC filter. This is using this approach. It's just due to the small amount of available pin for FPGA. So, and for the fun, sorry. I have just launched a specific application by providing a frequency, and it's all. And the PC do nothing, just connect with the SSH, and it's all. Everything is done in the Pluto SDR board. The reception, the processing, and the output on the audio sync. Now, to conclude, this is a flexible framework. Demonstration, we have demonstrated with some specific design end-to-end, but we have used our approach with the analog device environment to mix our approach and analog device approach, and it's definitively working. It's platform independent. It's possible to use with Altera, Xilinx, maybe other. It's respect the structure of a Linux system with where the IP is located is exactly as all controller around the core in the SOC component. Perspective, the first one is to finalize GNSS parallel gold code, verify and push on the GitHub for everyone. To improve the documentation, some part is quite, I suppose, well documented. There are some tutorials for FPGA, for Pluto SDR, but there are some missing parts around mainly TCL approach, and it's work in progress. And the final thing, currently for RISC-V seems to be important concurrent to ARM processor, so it may be interesting to try to demonstrate with a soft-core RISC-V instead of an hardcore ARM. Of course, we have the build-root extension for the FPGA. Again, same thing for the Pluto SDR with configuration, default configuration, a configuration with new radio already enabled, and of course the GitHub of the OscImp Digital GitHub where everything is available. It's just mandatory to git clone retrieve and to read doc tutorials to see how to start with this ecosystem. Thank you very much.
Questions? What do your kernel modules look like? Do you use UIO?
UIO. I use UIO. No. Currently, I use for some block I use the specific dev card device, but it's true I need to use IIO, UIO, or some specific structure of the kernel.
But you do most of the work in user space, right? Most of the work to control the FPGA IP is done in user space.
The configuration is done in user space by the user space.
Is it? Yeah, my question is how much of the configuration of the IP cores is done in kernel land and how much is done in user land?
The repetition between for configuration between user land and kernel land to configure the IP. Definitively the driver is know how to communicate with the IP, but depending on the IP, a part is done by the user space. For example, the NCO, you have an input frequency, you have an output frequency, you have the phase accumulator, and this is done in the user space through library. For the fear filter, you have just a set of data. You use the write on the on the file descriptor, and the kernel do everything about that. It depends.
From a user perspective, you don't need to touch the kernel. You get the drivers, and from a user perspective, you only put everything in user space.
Yes.
So you compared new Octave performance and your FPGA speed.
Sorry.
So you compared the speed of new Octave to receive GPS, and you compared your FPGA implementation to it. But did you also have, for example, like a radio flow graph to compare this decoder speed?
The speed comparison between the hardware implementation and the software implementation.
Yeah.
Finally, in the FPGA, we are just limited by the the sample rate. If the sample rate is 1 mega sample, we have 1 microsecond between two new samples. If you need to cross-correlate about 1 kilopoint, you have just 1 millisecond. It's not possible to reduce this because it's the FF front end, the limitation. And finally, it's not mandatory to speed up this because it's the fastest way, the fastest due to the input frequency. And the real gain is after that, you have result in the CPU, not you have sample to compute. It's just a latency in between the RF front end and the CPU. With a classical approach with Octave or you need to store a big sample data set, you process this. It's just the big difference. It's okay after it's possible to use the GPU to improve this, but you have always the acquisition time before able to process data.